Sorry. Okay, now we can start. Yeah, hello everyone. I am Edi Tribaswara. Good afternoon and welcome again to our Combinatoric Today series. First of all, I would like to extend our gratitude to the Faculty of Mathematics and Natural Sciences ITB for the constant support to this event. And also to everyone here, thank you for attending this program. Our big welcome to our speaker today, Professor Nick Wormald, one of the world prominent combinatorists from Monash University, Australia. Hello, Nick. How are you today?
Hi there. Yeah, good, thanks.
Okay, so thank you very much for your willingness to give a lecture this afternoon, and we really appreciate it. And we would like to mention that this program is brought to you by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi, Bandung, with the collaboration with the Center for Research Collaboration on Graph Theory and Combinatorics, Indonesia. And overall this year, we will have 14 editions for this series. And today is the 10th edition. And the speakers are all outstanding combinatorists from various countries. And now we are all very excited and honored to have Professor Nick Wormald from Monash University, Australia. And he will deliver a lecture with the title Uniform Generation of Combinatorial Objects. And this lecture will be chaired by Dr. Hilda Seaton. But before I give the control to Dr. Hilda, let us to have a group photo first. And to do that, Pak Adi will help us. Pak Adi, Adit?
Hello, can you hear me?
Yeah.
Yes.
Okay. Yeah. I invite you all to turn on your camera so we can take group pictures together. Let's wait for it. Okay. Okay, so maybe I will count from 2, 3. 1, 2, 3. Okay, once more. 1. Oh wait. 1, 2, 3.
Yeah.
All right. Thank you, everyone.
Okay, thanks, Adit. And now I let Dr. Hilda to chair this session. Bu Hilda.
Yes, thank you, Pak Edi. Good morning, good afternoon, and good evening, everyone. It is nice to meet you again in the Combinatorics Today series. It is a great pleasure and honor for me to be the moderator for our very special speaker, Professor Nicholas Wormald from School of Mathematical Sciences, Monash University. His talk title is Uniform Generation of Combinatorial Objects. Before we proceed, let me share with you the summary of Professor Wormald's curriculum vitae. It's already seen.
Yeah.
Is it the right one, Paidi? The
Okay, go.
right
Right.
screen. Yeah, right.
Perfect.
Okay, moment, please. Yeah, our speaker today is Professor Nicholas Wormald from the School of Mathematical Science, Monash University. Nick Wormald obtained his bachelor from the Australian National University in 1976 and PhD from the University of Newcastle in 1979. Currently, Nick Wormald is a professor at the School of Mathematical Science, Monash University. He joined the school as a professor and Australian Laureate Fellow in 2013. Before returning to Australia, Nick held position as a professor at the Department of Combinatorics and Optimization, University of Waterloo. And he also a chair in Combinatorics and Optimization. I should mention this, before Nick moved to Canada, Nick was a professor in Melbourne University, and I was his PhD student. I think I was the last PhD student Nick had in Melbourne Uni, right, Nick?
Not quite, but,
Oh, not quite,
but
right.
you were near the end there. You were near the end there.
Yeah, right. All right.
Yes. You were one of my first PhD students, really.
All right.
Yeah.
Right. Professor Wormald has published 244 papers in journals and conference proceedings, and has written 6 book chapters, and has collaborated with 165 co-authors. He has been awarded many research grants from the Australian Research Councils and the Natural Sciences and Engineering Research Council of Canada. Here are some selected recent papers, and you may have noticed that Nick's paper are quite long. All right. Professor Wormald was an invited speaker at ICM 2018. He was elected as a fellow of the Australian Academy of Science in 2017. He also received the Australian Laureate Fellowship in 2013-2017. He was a Tier 1 Canada Research Chair from University of Waterloo for, I think it's maybe about 11 years. And he was awarded 2006 Euler Medal of the Institute of Combinatorics and its application. Nick served as editor-in-chief of Journal of Combinatorial Theory, Series B, from January 2004 to December 2014. He is also a member of editorial boards of some major journals in combinatorics and graph theory. Nick's research areas are quite broad in combinatorics and graph theory, with some keywords, random structures, asymptotic enumeration, and computing algorithms. And for the last part of the summary, I would like to read a citation at election of Fellow of the Australian Academy of Science 2017. Nicholas Wormald is one of an elite group of mathematicians globally who combine the most advanced probability theory, combinatorics, and theoretical computer science to produce deep insights into the nature of random and complex networks. He specializes in random graphs and probabilistic combinatorics, graph theory, enumeration, the analysis of graph algorithms, Steiner trees, the analysis of real-life networks, and other areas in combinatorics, as well as the optimization of underground mine access networks. Wormald is responsible for an impressive number of major breakthroughs in these areas, and many standard methods used today were his invention. So now I would like to invite Professor Nick Wormald to deliver his lecture. Nick, the stage is yours.
Okay, thanks. I guess I'll share my screen now.
Yeah, right.
Yeah, okay. If I can find it, there we go. Okay, so
Yes.
can you see that?
Yes.
Yes, okay. Yeah, so let me know if the volume is okay. My
yeah.
volume is okay?
Yeah.
Yeah. Good. Okay, so yeah, I realized that I should have put random in the title perhaps, but when we're talking about random generation of combinatorial objects, the key thing that we're interested in is knowing what the distribution is. So uniform is the important word here. There's something funny about this. Wait a minute. It's not acting as usual. Anyway, we'll see how we go. So I'm talking about generating random objects where we want each object in a set to appear with the same probability. And the title is quite general, but I'll basically be talking almost exclusively about graphs with given degree sequence. But my first example will be something a little bit different. This includes research with various people. Just a minute, is it? Yeah, it's still okay. Okay. Various people who have contributed to some of the things I'll be talking about. I want to start with a simple example of how you can generate things uniformly at random with a quite non-trivial algorithm. Suppose we want to consider binary trees. So you have a left tree. Actually, my pointer is very slow. So here's a binary tree. And at each, there's a root vertex at the top. And let me just try to... Okay, a root vertex at the top, and there's a left subtree and a right subtree. But one of those subtrees can be empty. So these binary trees can be decomposed into the root vertex, the left subtree, and the right subtree. Now, one of those, it could be that instead of having a left subtree and a right subtree, you have an empty, just the empty tree, so no vertices. Now, if you know about generating functions, and I won't go into this in case there's people who don't know about it, I won't go into the details, but if you do know about generating functions, this decomposition lets you write the set of binary trees as the generating function as x, which stands for the root vertex, times the generating function on the left, for the left tree, the generating function for the right tree, plus the case that trees are empty is just a 1. So you have this nice generating function equation coming from the decomposition. And you can solve that equation, and that'll give you the generating function for these binary trees. And you can get the coefficient. Oh, there's the generating function. And you can get the coefficient using methods of extracting coefficients. So this tells you the number of binary trees with n vertices. Now, if you want to randomly sample a binary tree with n vertices, oh, by the way, if there's something that I'm assuming people know that that you think that maybe I should explain, that you're not sure about, then feel free to interrupt.
Okay.
Okay. Yeah. So one way to sample the trees is to compute the numbers of all the trees and then look at your tree that you want to randomly sample. If you know how many trees are on the left, how many possible trees are on the left with given sizes, and how many there are on the right with given sizes, then you can calculate the sort of distribution of how many trees have a given size on the left and on the right. And then you can randomly sample, choose how many vertices to put on the left side, randomly sample a tree with that many vertices on the left, and do the same thing on the right and put them together. So knowing the numbers lets you actually get a uniformly random tree. But computing these numbers, in this case, there's a nice formula for it, an explicit formula, but in many examples, you get recurrences that take n squared time just to compute. And running through the algorithm of choosing the left and right and so on, basically we can say that this algorithm takes around n squared time. Now there's a neat idea that Duchamp, Flageolet, Bouchard and Schaeffer came up with in 2002 that works for such recursively defined structures like binary trees, where there's a generating function you can develop by taking the structure into pieces and putting it together in the way we did with the two binary trees. And in this algorithm, you choose first an appropriate number x bar. And appropriate means that the algorithm is going to be quite likely to succeed. Now, this is an algorithm that if it fails, you just repeat. And you keep repeating, and when you succeed, what's produced is going to be a random binary tree with n vertices, or n nodes. And the way you define the random tree, you recursively do one of two things. Either put a node and recursively generate a random tree on the left and a random tree on the right. That's with a certain probability, which you can compute given your number x bar. And with another, that's the probability that it more or less that the next node branches and has children at all. And then with the other probability, remaining probability, you don't put anything. In other words, the node basically doesn't branch. Well, it's empty. That empty really means that there's no node there. So that cuts off one of these branches. Okay, so I won't go into the details of why this works, but it does give trees. Oh, the trouble with this algorithm is it gives trees, but since you're recursively deciding whether or not to add more vertices, and these sides are generated independently, you have no control over how many vertices are really produced. It's just a random number of vertices produced. But the nice thing is that if you condition on having n vertices for any particular n, then the trees produced are uniformly at random. Now, what you have to do then is choose this x bar to maximize the chance that the output has n nodes, because if it doesn't have n nodes, the algorithm fails and you repeat it. There is a simple formula for the probability of succeeding, and you can use that to optimize the chance that the tree has n nodes. Now, this might look like it's very you have to be optimistic for it to work, but there's some theory that says that for many classes of structures, of trees and tree-like structures, the complexity of this algorithm is quadratic. In other words, order n squared to get n nodes. So this is better than that previous method I mentioned, where you just count things, compute numbers, because you don't have to compute numbers in advance. But also, there are some cases shown by Sportiello recently where you can modify the algorithm and get actually linear time, expected linear time to generate the random structures. But that's for quite special classes of structures. Some others take time into the 3 halves. Anyway, so in summary, if you have a special kind of structure and you can write down this nice generating function, then you can do things quite quickly. And the optimal thing would be to get linear time. In other words, the time taken for the algorithm is a constant times the amount of data that it outputs. So a tree with n nodes has order n amount of data in it. Okay, so that's one type of algorithm that creates things, generates things exactly uniformly at random. Now, the rest of my talk will be about graphs with a given degree sequence. So I'm assuming you all know about what a graph is and what a degree sequence is. Okay, so we specify the degrees. Now, often for the interesting cases, we specify that all the degrees are equal to the same number d. That'd be a random d-regular graph, but we can specify the degrees to be different, and we ask for a random graph with those different degrees. But I want each graph with those degrees to occur with the same probability. So the problem is to sample uniformly at random from this set of graphs. So there are various reasons for doing this. People like to test algorithms. If algorithms have to run on graphs, then it's nice to know how they perform on various classes of graphs typically. And if you generate the graphs with a given degree sequence, you can modify the degree sequence to get different kinds of graphs and be able to say how your algorithm runs on these sorts of graphs. Many people look at networks and they ask, you know, for instance, social networks or migratory networks or food chain networks. And you can ask whether there's any competition going on in the biological networks or whatever. So you can ask how different are these networks from random networks with the same degree sequence. If you don't look for a random network with the same degree sequence, then you're bound to get completely different looking things. There's a connection with enumeration. A lot of methods for random generation are quite strongly related to methods for enumeration. And in fact, some of the strong enumeration results that I've got in the past for graphs with given degrees actually one of the main ideas came from an idea that arose because I was looking for a random generation algorithm. And it works the other way around as well. If you're looking for looking at enumeration, then some of the ideas can be used for the random generation. Now, how can we do it with graphs with given degrees? There's no recursive structure at all of the type for that Boltzmann type sampling that I discussed with the binary trees. So we have nothing like that going. What we do have as a basis for looking at graphs with given degrees is something called the configuration model, which I'll mention in a little while. Before that, I'll say more about algorithms for or earlier results for generating graphs with given degrees uniformly at random that do not use the configuration model. Now, there are the only other exactly uniform algorithms are ones of unknown complexity. Ones where you generate a structure. As you're generating it, you look at the probability it's being generated, and then you do a rejection. If something's going to be generated with high probability, if it comes out with a high probability, you reject it and with a high probability to bring it down to being accepted with a very small probability. And you can make that small probability the same for all structures. And one problem with this is it's very hard to get reasonable estimates of what probabilities to accept or reject with in order to work properly. And there's no really known complexity for how long it takes to generate graphs with given degrees using this sort of method. If you've heard of sequential importance sampling, that can be it's a special case of this sort of method. Again, unknown complexity. Now, that's the only ones that I'm going to mention here for exactly uniform sampling. All the others that I'm going to talk about use the configuration model. But there are methods, there are results on asymptotically approximate or approximately uniform sampling. So all the graphs produced with probabilities that are slightly different. In these ones here, the probability is close to the same for all graphs, and as the size of the graphs gets bigger, the probabilities get more equal. And these are fast algorithms, roughly linear except for log factors. I'm not going to go into the details of those. I'm focusing on exactly uniform. I'm just mentioning some of the other things that have been done. Now, Monte Carlo Markov chain is a method you may know about. If you do, then it's good to know that you can generate random graphs of given degrees sequences. If you want the deregular case where all the degrees are equal, then Jeremy and Sinclair have an algorithm that produces them. In this case, you get algorithms where the probability error, the differences in the probabilities can be made more equal just by running the algorithm longer. If you run it for long enough, you can achieve any small error, and that's for any size of graph. Whereas the ones on the previous page, the error is necessarily quite large when the graphs are small. As they get bigger, the error gets smaller. So, but by error, I mean the differences in the probabilities of different graphs occurring. Now, Cooper, Dye, Greenhill, and Greenhill gave results for regular and non-regular with these sorts of error of complexity bounds. They're very slow algorithms. At least they're provably what can be proved is that they converge or they get good errors within this time, but probably in truth they are much faster than that. They probably give almost uniform distribution after something like linear times log n time, but that hasn't been proved. So on the other hand, with the configuration model, as long as the graphs are not too dense, we can get much better results. And that's to get even exactly uniform distributions. Now, these ones up here work on the case that D is quite large as well as small. But for the configuration model, we have to have the degree basically at most root n. And for the irregular case, it's a different condition. Delta is the maximum degree. That must be big O of m to the 1/4, where m is the number of edges. Okay, so they're the sort of results that I'm going to be talking about. So we can actually get linear time for small enough degrees. So I'll talk about the configuration model, and then I'll say how we do this, how we do all this. So this arose from enumeration methods for bipartite graphs and then graphs. And in Bolabash's work, he gave it explicitly in this form, that you have sets of points. Okay, I call them buckets or whatever. And in each bucket, the number of points in each bucket is equal to the degree that you want for that vertex. Now the buckets are labeled, so we're going to end up with a labeled graph. What we do is take a random pairing of all the points in the buckets, okay? And then shrink the buckets to vertices, and you can see that the buckets with 3 points end up having degree 3. And the only problem is there can be loops and multiple edges, right? So if there are loops and multiple edges, then you don't get uniform distribution. But then on the other hand, often we don't want any loops and multiple edges. So what we do now is we focus on graphs with no loops and multiple edges. We want to generate those uniformly at random. Okay, so there's a simple rejection sampling method that can be used with the configuration model. What you do is you generate the multi-graph or this structure that comes from the configuration model, which might have loops and multiple edges. In other words, it might not be simple. So you reject it if it has any loops and multiple edges, and just start again with a new pairing up of all the points in the buckets. When you're successful and you have no loops or multiple edges, then you output the result, and that result actually will be uniformly at random. That's very simple to check. It's quite straightforward to do a check that every graph will occur that has the same number of pairings associated with it. And since each pairing is uniformly at random, then the graphs will be uniformly at random. Now, there's a problem with this. That is that the probability the graph is simple. So this is the probability that you accept it and you succeed and don't have to repeat. That probability is roughly e to the minus d squared minus 1 over 4 in the d regular case, and it's a similar expression for the non-regular case. Now, if d is 30, for instance, you want a 30 regular graph at random, then this thing turns out to be about 10 to the 15th times the number of atoms in the universe. That's at least by the current estimates of how many atoms there are in the universe. So computers would have to get very, very fast before they could repeat an experiment that many times. Okay, so that's not very useful even for d equals 30, and even for d equals 10, it's very wasteful. Now, we can improve this by using switchings, and this is something I did with Brendan McKay back in 1990. Suppose you do this pairing like this one at random, and there's a double edge. Then instead of rejecting and starting again, you can try to get rid of the double edge by choosing a couple of other edges and rearranging those 4 edges by putting other edges between the points in this way. So we can put these 2 edges and those 2 edges, and then the double edge has gone away. Now, this was uniformly at random in some sense. It was a random multigraph. It actually is a random multigraph having, given the number of double edges it has, which is 1 in this case, every multigraph with exactly 1 double edge and no other multiple edges and no loops, all of those would occur uniformly at random when you do these pairings. At least they all occur with the same probability. They don't occur with the same probability as simple graphs. That's the problem. That's one of the main problems. But anyway, so what we've done is got rid of that double edge. So we have some kind of random structure here. But given what we did, depending on how we do it, I haven't, described the algorithm exactly yet, but depending on how you do it, that thing won't occur uniformly at random. It's now a graph. There's no double edges. But in order to analyze what's happening there, we're going to think about that switching schematically. It goes like this. You have a double edge and you choose 2 other edges in the pairing and you swap the edges around this way, just so that the double edge disappears. Now, one trouble is that when you do that, there might have already been an edge between these 2 vertices. Okay, and then this would make a double edge here. Okay, so let's let SI be the set of pairings with exactly I double edges. Now, to simplify things, we're going to assume there's no other high multiplicity edges and no loops. And actually, we can get to that stage near the end of the algorithm. So that's not an unreasonable assumption. This is part of the algorithm, gets to a point where there are no high multiplicity edges and no loops. We just have some double edges and we want to get rid of them. But what we have is a uniformly random pairing of that type in this set. Then one of these switchings, if we do it validly with no extra double edges getting created, one of those switchings takes us to Si-1, where there's I-1 double edges. Well, how do we get uniformity? And in most of my discussion, I'll just assume that we're looking at the d regular degree sequence to make it easier. So we take a pairing in SI with I double edges, assuming it's uniformly at random, and apply the random switching. But if we created a loop or multiple edge, that would be invalid. So how would it create a loop? Well, I mentioned how it can create a multiple edge. If we choose edges like this, if we have a double edge and two single edges, and there's already one edge here, then you can create a double edge when you do the switching. And you could get a loop if you have a double edge and one of the single edges may be incident with that double edge. So when you do the switching, actually it creates a loop and something else. So those switchings are invalid. We don't allow those. Okay, so what we do is we choose a valid switching. And that valid switching, we don't choose a valid switching at random. So we start with the graph and we look at we look at each possible valid switching and we perform one of them. And each one we want to make sure it occurs with probability 1 over some number, constant n plus, where n plus is actually an upper bound on how many valid switchings any pairing has. So we look at all possible pairings in SI. We look at the maximum number of ways that you could possibly do a valid switching. And that just depends on choosing a double edge, then choosing a couple of other edges. So it's easy to write an upper bound on how many ways to do that. And write that as n plus. And then what we want to do is perform any one of the switchings with probability 1 over n plus. Now there's the picture to show what's going on here. We might have, in a very simple case, there's only 3 pairings here. One of them has 3 valid switching, or 4 valid switchings, and maybe 2 of them have only 1 valid switching. Then the upper bound on n plus might be 4. So if we're at this P here, we choose each one of these switchings with probability 1/4. If we're at one of these pairings, we have to choose that single switching with probability 1/4. Now, with the remaining probability 3/4, we have to reject and start the whole algorithm again. But the upshot of that is that every arrow here, going from a pairing in SI, every arrow here denotes a switching. So if you start from a pairing in SI and go to a pairing in SI-1, every possible switching of that sort is performed with the same probability, 1 over n plus, given that you're starting at the particular pairing on the left here. So the leftover probability here, with that probability, we reject and just start again, start the algorithm again. So if you look at the whole picture, the probability that, and you have a uniformly random pairing in the set of all pairings with I double edges, the probability that the algorithm is at that pairing at a given stage will actually be 1 over the number of pairings in that set, 1 over the size of SI. And the probability that it then takes a given switching will be 1 over n plus. So the probability, if you imagine the algorithm jumping in here to get a uniformly random pairing and then doing a switching, the probability it performs any given switching is 1 over n plus times the size of SI. So that's the same for all arrows here. In other words, for all switchings that switch into a pairing in SI-1. So now looking at the picture from the point of view of a pairing in SI-1, the probability, if this was the whole picture of all possible valid switchings, then this pairing would be getting generated with 3 times the probability of this pairing. The probability of getting generated is proportional to the number of switchings that create the pairing. Okay, so the probability that the pairing's reached is equal to the number of ways to reach it divided by or multiplied by the probability of doing any individual pairing, which is given by this denominator. So that's the probability of reaching any pairing here. So what we do now, we want every pairing here to be reached in the algorithm with the same probability. To do that, we have to equalize the probabilities. We reject with a certain probability. We want to accept the pairing with probability n minus over the number of valid switchings, where n minus is some constant. Now, once we've done that, let's not worry about the constraint on the constant yet, but once we've done that, the probability of the pairings created and accepted is the probability of transitioning to it times the probability of accepting, and we've skillfully chosen the probability of accepting here to cancel the F minuses and leave us with this thing, which is a constant, the same for all pairings. And the only problem is we have to make sure that when we accept, that probability has to be less than 1. We can't accept something with probability greater than 1. It can be equal to 1, but it must not be greater than 1. So the n minus must be less than this thing. But n minus we want to be a constant for all pairings in here. And so n minus has to be less than or equal to the minimum value of the number of switchings that lead to pairings in Si minus 1. So in this picture here, if these were the only valid switchings, then n minus would be 1. Well, that's actually an n minus here. Okay, so if we can do that, then we've created things uniformly at random, and we've moved from a uniformly random pairing in Si to one in Si minus 1, and everything's fine as long as the rejection probabilities are not too large. Well, that was just, as I said, just the last part of the algorithm. A similar thing happens to get rid of loops. So the whole algorithm looks like this. You take a random nice pairing, which has no loops, at most d squared double edges and no other multiple edges. That's what I call nice. Oh no, sorry, this isn't the whole algorithm, this is the last stage. After the loop, if you have such an algorithm, such a pairing, which you get to in the last stage after eliminating loops and other things, then what you do is that pairing will be in one of the sets Si, which we have no control over. It's just in one of those. And then what we can do is switch to Si minus 1 and so on, using the switching and the rejection technique. Where there was a probability of rejecting in the forwards rejection, in which case we restart, and there's also probabilities of rejecting in the backward rejection. And once you reach, but if you do reach Si minus 1 without rejections, then you continue with another switching, with another forward rejection possibly, or backward rejection, and so on. So usually what the algorithm does is it'll go down and move across through the switchings, and once in a while it won't make it to S0. But if it makes it to S0, there are no double edges, no loops, so you have a graph and it's uniformly at random. Okay, so that's the final stage, eliminating the double edges. Now the algorithm in full. What I just talked about then was this part here. Well, let me just, it's too slow. This part here was on the previous slide. So before that, we can use a similar, well, let's just start at the start with the random pairing. There's an initial rejection stage where if the pairing has created too many loops or double edges, we just throw it away. There's too many to deal with. Now that is quite unlikely. So with quite reasonable positive probability, or quite high probability, it's not rejected at this point. Any higher multiplicity edges are also quite unlikely. We can show they're unlikely as long as the degree is, the D, this is for the D regular case, as long as it's less than n to the 1/3. Okay, so if it doesn't restart, then we go into the stage of removing loops, which uses switchings just like the double-edged switchings, but a little bit different to remove loops. There's possibly a restart. If there's no restart, then we have a uniformly random pairing with some number of double edges and no loops, and then we use that last stage to remove the double edges, and usually we output the result, which will be a uniformly random pairing with no loops or multiple edges, which is the same as a uniformly random graph. Okay. Maybe if there's any questions on the way the algorithm works. No? Okay. Now the complexity is determined by the expected number of times you have to run through the algorithm before you succeed and don't get rejection, times the expected time taken of any one run through. Okay, going through all those switchings. Now, what we showed in 1990 was that the expected number of trials is bounded if d is big O of n to the 1/3. And the time taken to run through all the switchings is basically d cubed n. In our algorithm, in our paper, we showed how to do that in time d cubed n. And the difficulty is computing the number of switchings that create a pairing. Number of ways to do is, if you're given a pairing that's been created after a switching, and you've got to look at how many ways there were to create that pairing. Okay, and that's the difficult thing. And we have a result for that. Was McKay and I have a result for the non-regular case, as long as the maximum degree is not too big. Okay, so that's where we were then. Now, the crucial things that come up in looking at the complexity. First of all, to generate the random pairing, the time taken is a constant times the number of edges. That's quite easy. And if we want a linear time algorithm, we want the rest of the algorithm, after generating the random pairing, we want to do the rest of it in time constant times the number of edges. Now, the number of double edges, this determines how many steps there are in those switchings to get rid of double edges. It's usually around d squared, in the case of irregular graphs. We can assume it's constant times d squared. For each one, we need to compute the number of switchings creating the pairing. Now, I'm not mentioning loops here because loops are easier. There are not so many of them, and they don't come into consideration to determine the complexity. Okay, so very recently, really, Andrea Mann and Jane Gow and I introduced an idea that makes it easier to compute that F minus, that number of switchings that will create a pairing. A crucial observation is that the probability of creating a pairing in Si minus 1, that probability was the number of switchings that go into it. So if you do the switching like this, and then distinguish somehow the two paths that are created, then every pairing gets created with the same every pairing with distinguished paths gets created with the same probability. So the pairings with more pairs of suitable paths get created more often than the ones with fewer pairs of suitable paths, and they have more ways to distinguish the pair of suitable paths. So the pairing with two paths distinguished occurs uniformly at random. So what we can do is we can imagine a pairing with two distinguished paths, and now to be suitable paths, there's more conditions. There must be no edge between certain pairs of the paths, because those edges were all switched away in the switching. The switching starts with these edges and they all disappear. So between those two paths created, there's no edge between corresponding vertices. So we say, so to encapsulate all this, we say that the pairing is anchored at those two paths, and then the anchored pairings occur uniformly at random. Now, what we do now is basically de-anchor. Think of a pairing with two distinguished paths occurring uniformly at random. And what we want to output is a pairing in the same class without the distinguished paths occurring uniformly at random. So somehow we want to de-anchor, we want to forget what the anchor is, but that changes the probability distribution. Now we do it in two steps. We start with something anchored at two paths, we move to something anchored at one path. Okay, and then we move from something anchored at one path to something anchored at nothing, which means it's just the pairings are uniformly at random here. There's nothing distinguished. So I want to look at the second step because it's simpler and it's the same idea as used in the first step. To remove one of the two paths, to forget that anchoring, and we do the same thing. So we start with a pairing with a distinguished path of length 2. We want to produce from it a pairing with nothing distinguished. Now the pairing we produce is going to be the same pairing, it's just that we reject it with a certain probability, with just the right probability to make all the pairings have the same probability. You can do the same thing with a deregular multigraph. Okay, we can take this as a multigraph and just produce one with no anchoring. Well, the probability that a multigraph occurs is proportional to the number of valid two paths, which we can call pi2. It turns out that almost all the pairings have roughly the same number of two paths, valid two paths. Now, a valid two path in this case, just any two paths that doesn't use a multiple edge. There's no extra condition on other two paths being here. So how many two paths use a multiple edge? Well, that's something we could compute, and we know a bound on it. It's at most the number of double edges times the degree. So for each double edge, the degree, I'm assuming deregular here, if we get a two path using that double edge, the number of choices is big O of D. There's D on one side, or D minus 2 on one side, and D minus 2 on the other side. So what we do now is we accept the graph with probability equal to this pi2 divided by nt times d minus 1. Now, nd times d minus 1 is the number of two paths if there's no double edges. There's n vertices, and d ways to go from one vertex to another, and then d minus 1 ways to proceed to a new neighbor. So that's the number of two paths. I'm taking them in an ordered fashion here, counting them as ordered two paths, or directed. Okay, so what we do is accept G with this probability, and then what happens is that the probability the graph occurs is proportional to pi2. Then you multiply by this probability to be the probability the graph occurs and is accepted, and then wait a minute, let's see, pi2 is this thing. I just want to check, maybe this thing's upside down. Let's see. The number of valid two paths is pi2. No, actually, we want to accept with the reciprocal of this. We want that pi2 to cancel, so we call it n minus. Oh. N minus over pi2 of G. So that's the probability of accepting. Now, n minus, it won't be, I was trying to simplify things here, giving an explicit expression, but we don't have an explicit expression for n minus. So that's n minus is a lower bound on pi2 of G. For all G that we're interested in here. Okay, just like we were using before with the rejections on the backward rejections. So this is all the new way of doing the backward rejection step. Sorry about that. So when we multiply whatever the probability the multigraph occurs is proportional to pi2, and we multiply by n minus over pi2, then the probability it arrives and is accepted will be a constant. A constant for all, because the pi2's cancel, you get a constant for all multigraphs in the set of things we're looking at. Now, the probability of rejection, well, the important thing is how close can we make, this is the probability of accepting. We want n minus to be very close to pi2 so that we're accepting with a probability that's very close to 1. And it turns out it's so close to 1, the probability of rejecting is going to be order of I over nd. So basically to get n minus, to get the lower bound here, we take an upper bound on whatever this term would be. And actually a simple upper bound is probably just something like 2id or some such thing. Okay, so we can do that, and the probability, the important thing is the probability of rejection. Big O of I over nd, where I is the number of double edges in our graph. Now, what I mentioned before is that the number of double edges, we can assume it's around d squared, because if it's much bigger than that, we're rejecting that initial rejection. We never deal with graphs with more than 10 d squared double edges. So that means the probability of rejection is the order of d over n. And we know how many steps this is going to happen with. So then the probability of rejection overall is going to be 1 minus big O of d over n raised to the power d squared at most, or order of d squared, so constant d squared. And this is the most e to the minus, so 1 minus x is e to the minus x, e to the minus d over n times the constant times d squared, and we get e to the minus d cubed over n times big O of 1. So that's the probability of succeeding. So rejection occurs with this probability. So succeeding occurs with 1 minus that probability. And we want to succeed with cd squared times. So that's why I multiplied, took the power cd squared. So we can say the probability of not rejecting at all in the algorithm is e to the minus big O of d cubed over n. But we've assumed that d cubed is big O of n. So this is e to the minus a constant at most. Well, at least. E to the minus big O of 1, even if that big O of 1 is 10, we've got a constant probability there. So the probability of succeeding is a constant, so the expected number of times we have to restart the algorithm is a constant. So the total complexity is, again, the time to compute pi2 of g. Now, computing pi2 of g just involves computing the number of 2 paths using a multiple edge. And that turns out to be a very simple thing to do. To compute that, you find the number of valid 2 paths in the initial pairing. This is what we do. We can do that by looking right through the whole pairing in the start of the algorithm. And that time, you can do that in time order nd. Now, that's linear time. That's the time that we want the old algorithm to take. So we do that once. And then after each switching, we can update the number of valid 2 paths by doing a little bit of searching about what we change in the pairing. And we can do it each time in order d squared. And then the number of switchings we perform is order d squared. So the complexity is just order d to the 4th for that part of the computation. The complexity is order nd plus d to the 4th, which is d cubed, or nd as d cubed equals big O of n. We get linear time for that. which is the same as generating the initial pairing. Now that was looking at that second step. Remember, there were two steps in de-anchoring. One is where you go from two distinguished paths to one, and I looked at the second step where you go from 1 to 0. Now, it turns out that the first de-anchoring step is much more complicated, but using the same ideas, you can still do the whole thing. You can still do this step in each of the times you do a switching, in total time, big O of ND. Just using a similar ideas and some inclusion exclusion. So the conclusion from all that is that you can generate a deregular graph in time order dn if d cubed is big O of n. And there's a similar algorithm for general degree sequences where the constraint is the maximum degree is order m. What about reaching larger degrees? I just want to say a little bit about this briefly. The problem in the rejections, the reason we have to keep restarting is when our estimates for numbers of switchings, when the actual number of switchings are going in a certain direction, when that can vary a lot, then the number divided by, for instance, in the forward switchings, the number of switchings divided by the maximum number over all pairings, this fraction, if that's not close to 1, then we get a large rejection probability. And when we do that forward switching, we always have to reject if there's an edge there. So not long ago, Jane Gow and I found a way to allow a switching when the edge is there, so you no longer have to reject. You just create one of these things, which means you're moving from something with I double edges to something else with I double edges. And it turns out for the backward rejections, we had to introduce another type of switching to allow the failure probability to be much smaller. So in the end, instead of the old switching algorithm, which consists of continually switching and reducing double edges, we have a new one that sometimes actually switches and gives the same number or even less or even more double edges. But those other switchings occur with low probability. So in both cases, the algorithm, usually the normal path of the algorithm is to follow the big black arrows and output. And only sometimes does it do anything else. And the complexity there, well, Jane and I had complexity d cubed n, but using incremental relaxation now, again, the algorithm can be done in time dn plus d to the 4th. Now that complexity is linear if d is big O of n to the 1/3, all right? But if d is bigger than n to the 1/3, then it's no longer linear. It's no longer d times. So dn is linear because that's the number of edges, is dn. And there's a recent improvement with Oliver Reardon. Actually, there's a very slight modification of this algorithm that does all this, that can achieve linear time even when for any d little o of root n. And the slight modification is very simple. If you want to reject something with a certain probability that's very small, what you can do first is accept with a quite large probability that you know is smaller than the true acceptance probability. You can first accept with some reasonable probability, and if you accept, then you continue. And if you don't make that initial acceptance step, if that doesn't succeed, that's the only time you have to do any careful calculations and decide what the remaining probability is that you should be accepting. So it's just a very simple idea that actually can improve these results. Well, there are some other linear time results on graphs with, if you know about power law degree sequences, then some of those can be generated in linear time. And If you know about contingency tables, with given marginals, as long as they're sparse enough, then they can be generated in linear time. I won't go into those, they're just different applications. I want to finish up saying just about where we are at and what we might want to do next. We've had with Catherine Greenhill, Mikhail Isaev, and Nina Kamchev. I've been looking at generating in the non-regular case where the maximum degree is larger than we have so far. And this requires hundreds of new switchings, but it looks like it can be done with quite fast generation. All of a sudden, instead of using 2 or 4 switchings, we're talking about hundreds. So maybe it gives you an idea of the difficulty in going further. But still, there's remaining questions that are relevant. Is it possible to do linear time sampling in the non-regular case up to something comparable to the square root n we can do in the regular case? That's not clear. Even is it possible to do polynomial time sampling in the deregular case when the degree is bigger than root n? So it'd be nice if we could generate a random deregular graph where the degree d is around n over 2. But we don't know how to do that in any efficient way. Not uniformly. Not exactly uniformly. And then for power laws, this is, if you know about power laws, many power law situations occur with the exponent in the power law being less than 2.88, and it'd be nice to get lower than that. Okay, well, I think that's about the end of it. Yeah. So thank you for your attention, and I hope it's given you some idea of what we're up to with these random generation algorithms.
All right. Thank you so much, Nick. Yeah, okay. Actually, you still have some more time, but yeah, okay, that's all right. Maybe now we will have, before we start the QA session, I think we will have some song, Pak Edi.
Okay, yeah. So I would like to present some song. This is from the ITB senior and student choir, and Hilda and Rino belongs to this group. So this song is about folk song, composed from various folk song from various regions in Indonesia. So let me present the song. Just a moment. Yeah. Okay. Is it clear?
No, we can't hear the voice.
Huh?
We cannot hear.
Really? Let me. Okay. Try again. Yeah?
Yes.
Thank you.
Yeah, very nice.
I hope you enjoy the song.
Yes.
Okay.
Okay, back to
Yes.
Hilda.
Okay, thank you, Pak Edi. So now we enter the Q&A session. I already have two questions sent directly to me in Bahasa, and I will try to translate. But before that, maybe any other question coming from the audience? If who wants to ask me directly? Oh, yes, Afif, could you please turn on the
I
microphone?
already typed the question since my
Oh,
that is
all right.
not comfortable for a long question. Sorry.
All right.
Yeah.
So, Afif, would you like to ask directly, or I just read your question then?
That
Yeah.
will be fine.
Actually, Hilda, I can't. Your microphone is breaking up a bit for me.
All right.
So
Oh,
maybe
sorry.
I'll read the question. Can you hear me
Yes.
clearly? I could read the question,
Yes,
or you can say it.
Yeah.
The question
So,
I can
just
say it.
oh, yeah. Afif has problem with the internet connection as well. It's not stable. Okay, so there are two questions. The first one is, can the model and the result be modified to hypergraphs? This is the first question. And the second one, what makes the algorithm for irregular graphs can be very fast compared to generic graph sequence?
Yeah. Okay. So the first question about can it be modified to hypergraphs? Yes. The pairing model, the configuration model, works for hypergraphs as well, where instead of you taking pairs, you take triples or quadruples or whatever. And actually, I mentioned some work I'm doing with a group of 3 other people. We started by looking at hypergraphs, and certainly you can do similar work there. Some issues are a little bit different because mainly because with hypergraphs, the probability of getting what corresponds to a double edge is quite unlikely. It's quite unlikely that 2 edges, when there's several vertices involved, that all the vertices in the edges are actually exactly the same. So that's quite unlikely. So the important points to worry about in the algorithm are a little bit different from graphs. But basically, it looks very similar. The argument looks very similar. Now, for deregular graphs, it's a very good question you've asked. Why are deregular graphs special, and why can they be fast compared to other graph sequences where maybe even the degrees are less than D, but still the algorithms that we know of are slower? And the reason is that with deregular graphs, you can do a lot of tricks when you have to compute the numbers of certain little subgraphs in the pairings in order to work out the probability of rejection. And what happens with deregular graphs is you know in advance how many paths of length 2 there are, for instance, because you know the degrees of all the vertices. And sometimes you need to know how many paths of length 3 there are, for instance. In a deregular graph, there's n ways to choose the first vertex, and d ways to choose the neighbor, d minus 1 to choose the next neighbor, and d minus 1 to choose the next neighbor after that. And this is a rough calculation, and to correct it, you have to work out how many paths of length 3 are like in triangles and things like that, that are not of what you wanted to count. Now, for an irregular graph, how many paths of length 3 there are, it depends on how many vertices of 1 degree are adjacent to how many vertices of another degree. And you don't know that in advance. You have to start looking at the graph to decide what's going on there. And it becomes even worse when you realize that you need to know the numbers of these kinds of things that are near double edges. And for deregular graphs, a lot of this stuff is, you can make an initial estimate, and it's very close to the truth, and then you can calculate the corrections to it in some efficient way. But for the irregular ones, it's just harder. Okay.
Okay, thank you, Nick. That's question from Rina.
Thank you for the answer.
Okay, good.
Rina, could you please ask Nick directly?
Yeah, I can see. Well, I can see Rina's question.
Yes, but I don't know whether my connection is good because can you hear my voice clearly or not?
Yeah, yeah,
Yes.
Yep.
yeah.
So my question is about if we add more conditions to the graph. So in addition to the degree, for instance, if we want to know, we want to give the maximum diameter or maybe other distance parameter in the graph. Do you know any work that has been done in this?
Right. Well, for maximum diameter in particular, that one sounds a bit tricky. For instance, you could ask to generate a random Moore graph, couldn't you? And then no one knows some answers to that in all cases. So this model for generating the graphs for given degrees, that works for degree sequences. And if you want diameter in addition to that, well, that sounds sort of difficult. There are some things you can do if you really wanted to do something. You can try rejections, for instance. If you want bounds on something, you can hopefully generate the things and wait until you succeed. But that, of course, won't work very well for many problems where if the sort of graphs you're trying to generate are very rare, then it's just like looking for needles in haystacks. And I don't know of any natural way to incorporate the diameter into the algorithm. If it's not diameter, but things like the girth, if you want a random graph with a large girth, for instance, then you can use the techniques we've been doing. When you look at it, what we've been doing is getting pairings which generate a random graph with girth at least 3. So we eliminate the loops, which are cycles of length 1, and double edges, which are cycles of length 2. So you can actually we've thought about this, and you can eliminate shorter cycles as well, using a lot more switchings, but using the similar techniques. And we can do things. This is where incremental relaxation really makes a huge difference, compared to what we would have done beforehand, because you can do a whole lot of you end up with some anchors, a very large number of anchors, and you can eliminate them one by one quite efficiently. So that's girth. So you can eliminate short cycles, and you can get some results that are possibly interesting for large girth, not the largest possible girth that, say, a deregular graph can have, but maybe something like a half of the maximum girth, or maybe a quarter. I'm not sure which. But certainly the typical graphs have quite small girth, and so the ones with large girth are quite rare. But we can reach into that rare probability space by doing this switching technique.
Okay, thank you, Nick.
All right.
Okay, good.
Okay. Nick, there are 2 more questions written in Bahasa, so I try to translate it.
Okay.
The first one is, what other information can we get from the complexity function So is it actually the complete question is, apart from testing the algorithm, what other information can we get from the complexity function? That's the first question. And the second one is, can the complexity of algorithm be related to the probability of success of the algorithm?
Okay, the first one, I'm not sure about what information we get out of the complexity function. The bound on the complexity just tells us how fast the algorithm's running. All right. So I'm not sure, maybe that question could be restated for me to understand it. But the second one, can the complexity be related to the probability of rejection? Is that what it was?
The success of
The
the
success,
algorithm,
the
yeah.
probability of success. Yeah.
Yeah.
Basically, for the complexity of these algorithms, it's the average runtime. Okay, so there's always a chance that the algorithm keeps trying and trying and never succeeds for a very long time, although that's unlikely. So we normally calculate the expected runtime, and this is simply the inverse of the probability of failure. Wait a minute. No, wait a minute. It's the, okay, there's a simple formula. It's the expected runtime of one run times the expected number of times you have to repeat. Now, the expected number of times you have to repeat is actually 1 over 1 minus the probability of failure. Okay, so for a small, so it's 1 over the probability of success.
All right.
It's the expected number of times you have to run it. Okay, so that's the relation, I guess. So what's happened so far in the work we've done is that we put a bound on the size of the degree, and if we increase that bound by even a small amount, by doubling or tripling, then the probability of success starts going down very quickly. So we put the bound, and then at that point we've got a quite fast algorithm for, with the probability of success is a constant. And if we go much further, it becomes so small that the algorithm's going to become useless. So then the crucial thing usually is how long it takes to do one run until and to do the full number of switchings. And that's that's going to be what makes the difference between one algorithm or another when you look at the algorithms of the sort that we're looking at. Certainly the reciprocal of the probability of success is basically the number of times you have to run before succeeding.
All right. Okay. Thank you, Nick. Is there any more questions or comments for Nick?
Can I have one, Bu Hilda?
Yes, please, Patty.
Yeah, okay. I just thanks Nick for the very nice talk. I just would like to know if the algorithm we run many times, and what portion of the population that we can obtain from the result, from the algorithm. Is it possible to measure the portion of the population? For example, if we want to test some certain properties in this class, is it possible to measure the portion of the population that we obtain from this random algorithm?
What do you mean? What do you want? What do you want from the portion of population? So the algorithm takes a random sample each time, right?
Yeah.
Now, the population of graphs is very large.
Yeah, if we would like to know how much, what portion that the population can be hit by this algorithm as a result.
Yeah. Oh, so it sounds like you're asking basically how many graphs are there?
Yeah, different. Yeah.
Basically, yeah, we have asymptotic formulae for the number of graphs.
Okay.
Yeah. So they're very large. It's very large, right? So it's they grow faster than faster than standard exponential. It's more like factorial growth, even for 3 regular graphs.
Oh, okay.
Okay. It comes from you can calculate to work out the asymptotic number. What you can do is you can count the number of those pairings that I add. Now, if for a deregular graph, each graph is formed. Each simple graph is formed from d factorial to the n pairings. So you can write down the total number of pairings, divide by d factorial to the n, and then that gives you the total number of graphs if they were all simple. But they're not all simple, but we know the probability they're simple asymptotically. So that's actually an upper bound on the number of graphs. Total number of pairings divided by d factorial to the n. And it's very simple to write down the number of pairings of dn points. Dn factorial over dn over 2 factorial to the dn over 2. So anyway, when you look at all that, you get some factorial sort of growth in the number of graphs.
Okay, thank you.
It's a huge number, yeah.
Yeah.
All right. Is there any more question for me? Okay, then. I think once again, we thank Professor Nick Wormald for a very wonderful and inspiring lecture. Thank you so much. Now, I will hand over the program back to Professor Baskoro.
Okay. Yeah. Okay. So thanks again to Professor Nick Wormald for a wonderful and inspiring lecture. And on behalf of the Faculty of Mathematics, Natural Sciences, we would like to present Professor Wormald a certificate for this for giving a lecture in this event. Let me show the certificate.
Right.
Okay, just a moment. Yeah. Okay, so this is the certificate that Professor Nick Wormald will have this, and then we also to present this thank you note with the caricature of Professor Nick Wormald photos. I hope Nick enjoy this painting. This is my student paint this your picture.
Well, that's nice. So thanks very much. Although you might have to recolor the hair.
Yeah.
Based on your previous photo. Yeah.
Okay.
Not the current one.
Yeah.
So we will send you both document, through the email. Okay, so thanks again, Professor Nick Wormald, and also to everyone here attending this lecture, and see you next 2 weeks. Yeah, Professor Akihiro Munemasa, thank you, and thank you, everyone.
Yeah. Okay. So I wanted to say thanks again for the invitation, and thanks very much for the singing choir interlude. That was extremely interesting. I can see Hilda.
Did you recognize Hilda and Rino?
I could see Hilda in various places wearing something on her head, sort of like.
Yeah, that's right.
Yeah, but Reno is somehow. I think I saw her at one point, but the it was hard to see her. I didn't see her after that. So I think. Yeah.
Okay.
That was
Okay.
good. Thank you.
So, terima kasih, Nick. Yeah.
Okay.
Thank you.
Okay. Bye then.
Bye-bye.
Bye everyone.
Okay,
Yeah.
bye-bye.
Thanks a
Yeah.
lot. Yeah. Bye-bye, everyone. Yeah.
Bye.